Hello, I am Adrian Hendricks, and today I will present you our work on differential privacy for gossip protocols. This is joint work with Aurélien Belay from INRIA and Rachid Garawi from EPFR. So the basic algorithm that we will consider is a very simple rumor spreading algorithm. So we have a source, Alice, for example, which would like to transmit a rumor to her friends. So here her friends are Bob, Charlie, and Diana. And the idea is that Alice will tell the message to someone, and then someone else will wake up and tell the message. So more formally, we assume that people wake up at discrete times and choose a neighbor uniformly at random to communicate with. So, for example, at the beginning, only Alice knows the rumor, so Alice wakes up and then she informs Bob. Then, at the second time step, Alice and Bob both know the rumor, so we pick uniformly at random between Bob and Alice, and we assume that Bob is picked, and so now Bob chooses a neighbor uniformly at random again, and Bob will pick Charlie, for example. So the second message is sent from Bob to Charlie. Now we just rinse and repeat. We have three people informed, so Alice is picked, 1 out of 3, and then she again picks a random neighbor, and this time it's Charlie again. And last message, Bob wakes up, he picks Diana, and now Diana gets the message and everyone is informed, and so the algorithm has ended, basically. So now the question we ask is how private this procedure, this gossip algorithm is. And in order to know the privacy guarantee, well, we need someone to learn something. So in our case, we will assume that we have a subset of curious nodes. So there can be many curious nodes, but in this example, it will just be Charlie. So we assume that Charlie is curious and that Charlie would like to know who started spreading the rumor. So he received messages from Alice, he received messages from Bob, and so he would like to know who started this. And so the main question we ask in this setting is this protocol private, and in what sense? So we know that Charlie cannot guess the identity of the source with certainty. So the protocol guarantees some privacy. It has natural guarantees because the answer is never sure. But we would like to have a more quantitative answer. So, for example, what is the probability that Charlie identifies the source? So that would be a more quantitative question. The problem is that this probability actually depends on the attack that is chosen. So it depends on how Charlie decides who's the source. The other problem is that it's not resilient to side information at all, because the probability that Charlie identifies the source will depend on what Charlie knows. For example, if Charlie knows that Bob cannot be the source, then with more probability he will say that Alice is, and we will have poor privacy guarantees in this case. So we would like more robust definitions. And before we get into these more robust definitions, we'll just quickly talk about what does Charlie see. So the sequence of messages that we've presented you is first Alice sends a message to Bob, then Bob sends a message to Charlie, then Alice sends a message to Charlie, and then Bob sends a message to Diana. So the sequence of all messages that have been sent in the network that we call as omni, like as if an omniscious entity could see all messages, is this sequence AB, BC, AC, BD. But now, from the point of view of curious nodes, so here it's only Charlie, but it could be more curious nodes. We can imagine that Bob is curious as well, or Diana. But if Charlie is the only curious node, then the sequence seen by Charlie is BC and AC. So Charlie just sees that first Bob sent him a message, and then Alice sent him a message. And so, based on this, on what is seen by Charlie, so the output of the protocol as seen by Charlie, we can now introduce our definition of differential privacy forecasting. So, in an informal way, we could say that if we fix two arbitrary nodes in the graph, Alice and Bob, then the probability that the curious nodes receive messages in a given order, so for example, Bob sends to Charlie and then Alice sends to Charlie, should not be too different whether A or B is the source. So this means that if you fix two nodes in advance, then the output should not depend too much on whether A or B is the source. So put another way and more formally, it means that if you have a set of possible output sequences S, and any set of possible output sequences S should verify that the probability that the output belongs to these sets, knowing that Alice is the source, should be smaller than exponential epsilon times the probability that of the same outputs, knowing that Bob is the source plus some delta. So epsilon control how different two probabilities can be for any event. So we like epsilon to be small because it says that such events, even if Alice is the source compared to the case when Bob is never, like, I'd say 2 times bigger, for example. It's never more than 2 times more likely to happen if Alice is the source rather than if it's Bob. And we have this delta variable, which actually is a relaxation of differential privacy, and which gives you some slack. And what delta does, it allows some outputs of maximum probability delta to be much more likely if Alice is the source than if Bob is. So if we have, for example, some outputs that could never happen if Bob is the source, well, as long as they're really not likely, so as long as they have probabilities delta delta, we'll say that this is okay, basically. And what's nice with this definition is that it's independent of the attack. It's very robust to side information, and it guarantees composability. So if you spread multiple rumors, then you have guarantee on that as well. So it's good. It leads to very strong guarantees, but the problem is that it's sometimes a bit hard to show and a bit restrictive, as we'll see. So the protocol we'll study is the protocol I showed you with a slight twist, which is that when a node sends a message, it has a probability S to remain active. So this is what I showed you. At each round, and each time a node sends a message, so we first sample uniformly at random within the set of active nodes the node that will send the message. Then, with some probability 1 minus s, we remove this sender from the set of active nodes. So this node will no longer be active with some probability. And then we sample the receiver uniformly at random from the other nodes. So I should say, and this is quite a big caveat, that this work is only for complete graphs. And I invite you to look more at the paper for the case of general graphs. I'll talk about this later. And so you sample the receiver uniformly at random, and then what you do is that you add this the receiver the node that received the message to the set of informed nodes and to the set of active nodes. And then you just iterate that until all nodes are informed. So to illustrate this, if you have s equal to 0, which means that each time you send a message, you only send one message, you deactivate. So the source, it's this case here, the source first sends a message and then deactivates. It's no longer read. And then this node is active and it will send the message to another node. If s is equal to 1, then the source sends a message to another node, and then both nodes remain active, and both nodes will send new messages. But now we can also take s to be 0.5, for example. And so in this case, s sends the first message, then say flips a coin, it deactivates. Then the new node sends a message again, but this time it remains active. So at the next step, we actually have 2 active nodes at step 3. So that's basically how things work. And now we'll give privacy guarantees for this algorithm. The first result that we show is a rather surprising result. So it's a result on the standard push algorithm. So the one that I presented you at the beginning with Alice and Bob, in which nodes keep emitting. And it basically relies on the fact that when the graph grows, if we fix 2 nodes in advance, then the probability that the node that is not the source learns about the rumor in some times grows with the size of the graph. I mean the time needed so that the other node knows about it. Whereas the time needed for the source to communicate with the curious node, this doesn't scale with the size of the graph, is the ratio of curious nodes is constant. And so this leads to the following theorem, which states that if the standard push algorithm, so when you take an s equal to 1, so nodes never deactivates, guarantees epsilon delta differential privacy for all values of n, and for a constant curious nodes ratio f over n, where f is the number of curious nodes in the graph and n is the size of the graph, and constant epsilon, which is not infinity, then delta has to be equal to 1. And so this means that standard push is very fast, but its privacy guarantees are actually void in the limits of large graphs. On the other hand, you can consider the case in which s is equal to 0. So this means that you communicate once, and then you stop emitting until you receive the rumor again. And in this case, we'll have very strong privacy guarantees, because you actually forget the initial conditions in one step. Since the graphing is complete, then after the source communicates for the first time, then only one node is active, and it's not the source. So basically, you're okay. And in terms of differential privacy, it means that for any epsilon greater than 0, then muting after infecting, so taking s equal to 0, satisfies epsilon delta differential privacy with delta equal to f over n, so the ratio of curious nodes, time basically something barely smaller than 1. And the good thing is that this is actually optimal among gossip protocols. So I invite you to read the papers for the detail of this, but basically with any reasonable algorithm, you cannot guarantee more than this. So it has optimal privacy guarantees, that's great, but it's very slow because only one node is active at any time step. So it will take a lot of time for the algorithm to converge. So the situation is actually the following. On the one hand, you have the muting after infecting algorithm with s is equal to 0, and it guarantees a lot of privacy, so it's very private, but it's very slow. It takes time proportional to n log n to inform all the nodes in the graph, because only one node is active. So this is terrible. On the other hand, you have the standard push protocol, which informs everyone in times proportional to log n. So that's nice. But the privacy guarantees are basically void. I mean, if the graph is large enough, then you cannot guarantee any reasonable level of privacy, and that's not satisfying. So what we hope for is for a trade-off. I mean, there's this whole square in between, so we know that we can't go faster than this, we can't do more private than this, but we have this whole square, and where can we go in this square? And the answer is basically to take S between 0 and 1. And this really allows you to actually hit the trade-off that you would like to hit. And so this is shown by the following theorem, which means that if you fix some muting parameter S greater than 0, strictly greater, then for any epsilon, the parameterized gossip algorithm that I showed you is epsilon delta differentially private with delta smaller than S, so the probability of continuing to emit, plus 1 minus S f over n. So f over n is the fraction of closed node. So actually, the bound is a little finer than this, but this is like the easy to parse version. And it's just a convex combination between the essentially optimal f over n guarantee and the S1 guarantee. And so we can guarantee reasonable levels of privacy, so that's great. And at the same time, all nodes are informed in time big O of 1 over S log n. So this is great because we recovered this fast logarithmic spreading time, so which is what we wanted in the first place. So this means that parameterized gossip can obtain near optimal privacy guarantees, granted that S is not too large, with a spreading time that is logarithmic in n instead of n log n. So the speed result is a bit challenging because the number of active nodes is no longer an increasing function of the number of rounds. So you have to be careful because you can have less active nodes at one round than the previous one. Otherwise, the result is really easy to show. And for the privacy result, you need to condition on the right event. Basically, the fact that you communicate with the curious nodes before you deactivate. So you can look the details into our paper. I invite you to do so. And the good thing is that now we've actually hit the trade-off between the two. So we can have a non-trivial delta with logarithmic spreading time. So the question that remains, and we haven't answered, is this optimal? So we know that we can't do better than this square. So this square is the feasible region. Can we hit the trade-off a bit more on the right? We don't know. Conjecture not, but I mean, who knows? Now I'll just finish with some empirical results, just to show that it's actually important to have differential privacy in mind when designing an algorithm. So here is just a very simple experiment in which we show the attack precision under prior information on the source. So this means that the curious nodes, they know that a fraction of the nodes actually are not the source. So they do not suspect a fraction of the nodes. And then, I mean, you can see the details in the paper, but the way to go for the curious nodes is just to say that the source is the first node that communicates with them. And in this case, so the blue line is when only 1% of the nodes are suspected, and we have very bad privacy guarantees. And then the orange line is for 10%, green line is for 50%, and the red line is without site information. So all nodes are suspected. And we see that when s is equal to 1, so standard push, there are very big differences between the red line and the blue line. So the case in which all the nodes can be suspected versus only 1% of the nodes are actually suspected. Whereas if we have small n's, well, the privacy guarantees improve in all cases, but they improve a lot for the case where only 1% of the nodes can be suspected, and the guarantees they actually match. They do not depend on the site information so much quite quickly. And then if s is equal is very small, then we almost hit the 10% limits, which is actually the number of curious nodes in the graph. So we know that we can't do better than this. But what's important is that when the muting parameter is small, background knowledge only marginally improves the power of the attacker. Whereas when S is large, it really improves it. So we have other experiments similar to this one that show that it's really great to have differential privacy and robust guarantees in mind when designing algorithms. So the main takeaways of our work are that differential privacy can be adapted to assess the guarantees of gossip protocols in a robust way, and that it can be used to actually design algorithms. That fan-out-like mechanisms allow to improve guarantees by preserving the logarithmic spreading time, because the probabilities to stop emitting can be seen as some kind of randomized fan-out. And so I've already said it, this is only for complete graphs. The question of extending this to arbitrary graph remains open. It's a very important question, but it actually requires a relaxed differential privacy definition and adversary model. So we talk about this in our paper, and we have a whole part of the appendix dedicated to this, which I encourage you to read. And finally, we can also reverse the problem and use this to design systems in which we have guarantees to detect the source. So we know that whatever happens, the source can be detected. I mean, the signal is here to detect the source in order to find patient zero problem, because rumor spreading is very tightly linked to spreading of an epidemics, for example. So thank you for viewing the video, and I hope we'll chat soon during the conference.